All right, so we're going to look at one of the examples from the book. So this is example 5 on page 366 of chapter 6, example 5. I would encourage you to get your book out and follow along so you can read the question in sort of detail. So you read over the question in detail first. All right, so here's what we got. We got some moose here because it's the Upper Peninsula of Michigan where they have a lot of moose. All right, and so here's what we have: some differential equation that describes the moose growth, the population of the moose. All right, so I've written that here. So our first question, question A, says, what is the carrying capacity? So carrying capacity. So this is just a matter of being familiar with this equation and knowing that the number that appears in the binomial here, that is the carrying capacity. What does the carrying capacity means? It means you cannot have more moose than that. If there are more moose than that, then they're all going to die off. So, well, they'll never get to that point because as they start to get near a population of 1,000, their reproduction rate is going to drop off until they're not producing anymore. So they're never going to get to 1,000. All right, then they certainly not going to get over 1,000. So that's called the carrying capacity. It's also, the maximum population is another way to think of that. That's why they use M for it, maximum population. So in our standard equation, dP dt equals K P M minus P. That's just our standard equation. And so the carrying capacity is the M. That's all. All right, so we're going to say that the carrying capacity is 1,000. That's all. All right, a question that they did not ask, but which they will ask in some other questions. At what population will the maximum growth occur? So I just want to point out again that the max rate of growth, all right, the maximum growth. So dP dt is a max. dP dt is max. So the maximum rate of growth occurs at m over 2, is when the population, not the time, but the population is m over 2. So when there are 500 moose, that's when the population is going to increase the most rapidly. Okay, less than 500 moose, there's not enough of them to reproduce rapidly. More than 500 moose, they're starting to approach carrying capacity, so they're going to start dying off of disease and food shortages and such. All right, not pleasant, but hey, it's biology. Part B says, with a calculator, generate a slope field. So there is some, you can generate a slope field with a calculator, you can generate a slope field with Desmos, and maybe we'll look at some of those later. I don't find any of them to be terribly great or useful. I have not really had recourse to using technology to drawing a slope field because, the interesting ones, you need to find them somewhere. So for example, here's a slope field for this one. All right, this is a slope field for the moose. So it says it's 0 to 25 by 0 to 1,000. So this is 0, 1,000, 0, 25. Right? It's not clear. The 0 to 25 must be the x-axis. So that must be time down here. I mean, they're not terribly clear about that. I think this is time down here, 0 to 25. This is population 0 to 1,000. The maximum population is 1,000. So just looking at this slope field, there's actually interesting things that you can see. So one of the things that's interesting is, notice how every column is a carbon copy of the column before it. The reason for that is that if you look at the general differential equation that this comes from, P is your independent variable here. So P is basically like, P is like Y. Sorry, P is your dependent variable. It's the population. All right, so the independent variable is time. And this is dP dt, so it's actually basically like dy dt. All right, so the rate of change of the population is proportional to the population amount. So the dy dt, if you think of it in terms of x and y, because you're looking at a graph, the dy dt depends on the y, but notice that t does not appear in here. The variable t does not appear. T is the independent variable. So what you see in terms of the graph here is that all of the vertical columns are the same because the equation does not depend on the value of x. Or, here we could call it the value of t, but we're used to thinking of the function in terms of x and y. So the dy dx, if you think of it that way, does not depend on X. It only depends on Y. So we can see the rate of change increasing and then decreasing as we go up, right? So it starts slow, increasing, and then decreasing as we go up. But as we go across, it just stays the same. And that's because the rate of change does not depend on the variable t. It only depends on the variable p, which is like the y. So this is p-axis, this is t-axis. All right? So that's one thing. And then other things that you can notice about this is, so up here at the top of the graph, because this is 0 to 1,000, so this is 1,000 up here. It would be nice for them to label that, right? But they didn't. This is 1,000 up here, all right, at the top. So if you look at the rates of change, this is like shallow, little steeper, little steeper. Here's our steepest slope right in the middle, okay? So your steepest slope, your greatest rate of increase occurs at the middle of the population continuum. So here's our maximum population, here's our minimum population. Up here at the high populations, our dPdt is not high because we're having a lot of reproduction because there's a lot of moose. However, they're near the carrying capacity, so they're incurring disease, predation, and resource scarcity. So they're dying as quickly as they're being born. Whereas down here, there are few of them, so they're not reproducing very rapidly. But what you have in the center is sort of a sweet spot where you have enough moose that you have a lot of reproduction going on, and yet you have not approached the carrying capacity, so you don't have as much predation, disease, and resource scarcity. So right here in the center is sort of the sweet spot of reproduction where you have the maximum. All right, so this is just like looking at the slope field. This is with a calculator generated slope field. I never even learned how to do that. YouTube it if you want. I've never found it useful. But you know, if you want to find one, here's a useful one. All right, here's a one with a particular solution drawn through it. So they've drawn with a particular solution. All right, and you could, so this is your typical logistic curve. And you can see the logistic curve starting out flat. And so one of the things that goes on is that down here, as when the population is small, you see what looks like exponential growth. But then what happens as you hit m/2, the maximum rate of growth, is that there's an inflection point and the growth rate drops. And then you start to flatten out up here. So a lot of things that appear to be exponential at first, because you're in the inception of the phenomenon, can turn out over time to actually be logistic. I think a lot of the errors we make in analysis of sociologic phenomenon, like take even technology, right? So we think of technology as having exponential growth. If you think of like cell phones, right? When they first came out, more and more people had cell phones. Their capabilities were increasing exponentially. You had flip phones, and then they started to have internet phones, and then they got 1 billion apps on them, and they can access the internet, and they have all these specialized apps. So they're like really looking like they have exponential growth, right? But now think about now, where like for the past 5 years, have your phones really changed that much? They've gotten higher resolution cameras, they've gotten more memory, but the essential function of the phone has not changed. So even in terms of technology, you have things that look like exponential growth, but then they start to flatten out as they reach sort of a plateau. I think that happens with a lot of things that we imagine to be exponential at first. So this occurs with population growth too. So that's where it was first observed. It was exponential population growth, but that can't go on forever. So eventually that population is going to flatten out. Or if you think about infection with diseases, like we're down here in terms of COVID. We're like way down here. So everything that we're looking at looks like exponential growth, right? But if we ever got up here to half the population being infected, which is when you would have the maximum transmission rate globally, all right, we're not even close to that right now. Not even close. But once that happens, then the infection rate, this is assuming we do nothing, right? There's no vaccine, nothing. Then once half the population is infected, then the infection rate starts to slow down because half the people are already infected, so you can't infect somebody who's already infected. So then the transmission rate starts to drop off until essentially everybody's infected. That's the theory of so-called herd immunity, without vaccine herd immunity. Of course, the problem is we're down here. We're really only at the beginning of this epidemic, and there's already globally 2.25 million people dead. So if you allow the transmission rate to get up here to where it starts to have a natural inflection point instead of doing something about it, you wait till it has a natural inflection point, you're going to be looking at 40, 50 million people dead before that happens. That's why it's so important to engage measures now while we're still down here, because you don't want to be up here because there's too many dead people. So, but all the models they're using now are exponential, because down at the lower part of the curve you see exponential growth. Then things start to flatten out as we reach a carrying capacity. So all this is about carrying capacity. It all emerged from fairly recent work in biological science. It's all very interesting and important. All right, now that's a lot of dialogue around this example, but we haven't actually started to do it yet. So, but those are all important observations, things to understand about the logistic growth model, in particular that your maximum rate of growth occurs when the population is half of the carrying capacity. And we'll use that a couple of times in some of the examples. All right, next, we're going to actually carry through this example and see what we can find for the equation for the function. Because this equation just describes the rate of change. It doesn't describe the population of moose, only the rate of change of the population of moose. If we want an equation describing the population of moose, we have to solve this differential equation. That is what is next.